All right. Yeah. So what today's going to be is at least my planned part is I picked one of the practice exams. I picked the one that didn't have the kind of solutions going with it. So I think there's an exam to practice in there. So I'll leave that. So anyone that wants to work that out and then, or try it out and then see what the solutions are, you'll still have access to that. And this is a different version that doesn't have solutions to it. So in this, there's a solid of revolution. There's an arc length problem. There is what will turn out to be an improper integral, a different kind of improper integral, and then another solid of rotation. I guess the way to start is, are there any of these topics or other ones that anyone would especially like to see, just to make sure that we touch on things that people would actively want before just kind of jumping around and getting some of the other topics? All right, so then if as we're going through this, at any point you think, oh, I'd like to see another one of this, or could we try something a little bit different? Let me know. I'll be happy to switch gears and find a different problem. I've got a big textbook here that I can pull some examples from. Or any of these problems that you'd like some more explanation, definitely let me know. Okay. So starting with problem one. So here we're forming a solid by rotating the region, the squared or bounded by these four curves. Well, three of them are lines, and then the square root of x curve. So we have the square root of x, y is 0, x is 1, and x is 3, and we're rotating this around the x-axis. So for these problems, while you might be able to do it without the graph is really, I think, key to understanding what all the pieces are and how they're fitting together. And the kinds of functions we'll be rotating will be sort of basic functions, maybe shifted a little bit, but some standard shapes that are not, where it's not too much to ask you to know these shapes. There definitely won't be anything really complicated. It'll be the kind of standard functions, maybe shifted a little bit. So the square root of x is our sideways parabola, looking like this. And so then our other lines, y equals 0 is the x-axis. So let me draw this. Y equals 0, x equals 1, x equals 3. And so we have this kind of shape here, and we're rotating around the x-axis. So when we're doing this, what we really need to, or the way we can start it, and there might be different ways of going about this, but the things we really need to know are, to set up the integral, is this a dy or dx integral? Once we've decided that, what are the bounds we're going to use? And then once we know that, or those pieces, what are we actually integrating? So in this case, we're going around the x-axis, and we're always integrating along the axis. So this direction, moving horizontally, says this is going to be a dx integral. And so since we're moving along in the x direction, we're going from this left edge of our region to the right edge of our region, and we don't need to do any extra work for those. Those are these x equals 1 and 3 that were given. So then comes where typically most of the work is, and we need to know the radius. In this case, we're also not having to do a lot of extra work. Our radius is the distance from the axis to the edge. Worth pointing out that because our solid is right up against the axis, this is the disk method, not the washer method. There's no hole in the middle that we have to deal with. So then with all these pieces, we can say, well, we're integrating from 1 to 3. It's a dx integral. Then there's a pi times the radius squared. The radius is the square root of x function. And with a little simplifying, this is pi times the integral from 1 to 3 of just x. And so we can do this integral. I might not go all the way to the end, like what gets put in your calculator, but use the power rule to get x squared over 2. That's from 1 to 3. So this is 9 halves minus 1 half. And this turns out kind of nice. Combining the fractions, we get 8 halves or 4. So this gives us 4 pi. Okay. Questions about this problem? Okay. So I think this one is the most standard version of these disk method problems. We've seen the kind of some different variations, and I can pick out some of those if you'd like, but this is the basic process that you need to be able to do. Okay. All right. Then let's see, preferences for other questions. We can keep going through it all the way. Next up is arc length, or I can jump around a little bit if anyone would like. Okay. All right, so then we can do the arc length here. Yeah. So the arc length formula is for some function f of x, some curve from x equals a to x equals b. This is the integral from a to b, and then the square root of 1 plus the derivative all squared. Okay. So then this is what we're going for. Our function is this y equals x cubed, or well, sorry, not x cubed, x to the 3 halves. And so that's what we're going to take the derivative of. So we have the integral from 0 to 4, the square root of 1 plus the derivative of x to the 3 halves, that's a power rule. So 3 halves, x to the 1 half, all squared dx. So then squaring this, the biggest simplification is that we cancel this 1 half power, but we still have some things inside here. So this is 1 plus 9/4 x dx. When we get here, something to keep in mind, which can help, is if you're asked to actually find the arc length, you have the tools to do it. Sometime or an option might be if I say set up the arc length integral, don't worry about integrating it. In that case, the functions can be a little more complicated, but if you're asked to actually find the length, you need to be able to do the integral. In this case, what we can do, the most way to be the most careful about it is maybe do a u substitution. It won't be a big one, mostly keeping track of these constants, but it if you don't see how to deal with the constants right away, take the extra step and do the u substitution. So if u is the entire inside, and this is what we want to do because its derivative is going to just be a constant, and that'll be easy to manipulate with u substitution. So then the derivative is just the 9/4. We have the dx in here, so we multiply by 4/9 or divide by the 9/4 to get just dx on one side. So the integral that we're left with, maybe forgetting about these constants for a little bit, or you can convert these constants to u by putting them into this equation here, but I'll just find the antiderivative first. So we get the 4/9, which is coming from there. Then we have the square root of u, replacing the inside part with u in our equation, and then du. And now we can use the power rule. So the new exponent is going to be 3/2. And then we divide by that 3/2. And so we have to combine these constants together. Dividing by 3/2 is multiplying by 2/3. Combining the fractions that we get is 8/27. And it's u, which is 1 plus 9/4 x to the 3/2 power. So that's our antiderivative. And then we can come back and say, well, in the context of finding this definite integral, we have our antiderivative, 8/27, 1 plus 9/4 x to the 3/2. We're evaluating this from 0 to 4. And so we'll get something which we're going to have to stick in a calculator, but for now we'll say put in 4. The 4's cancel and we get 10 inside the exponent. So this is 10 to the 3/2. And then if we put in 1 or put in 0, we just get 1 on the inside. 1 to a power is 1. So we only get the 8/27, or just a placeholder 1 if I factor that out. And so this is 10 to the 3/2, not 32nd power. Questions about this problem? Okay. So in this case, if you're studying, this is one where I'd put a little more emphasis on looking at the different examples we've done and seeing what integration or what the integration has looked like. Because in here, there's a formula. You do need to know that this is the formula, in particular, that it's the derivative being squared, not just the function. But once you get the integral set up, for the problems that want you to find the arc length, it really quickly just turns into, here's an integral, I need to do it. And because these are the form of these makes them a little difficult to deal with, you want to look at examples and see what are the different strategies. And this is one way. If you end up with a linear function on the inside, so no powers, no fractions or anything, just the equation of, for the a line basically, then u substitution will let you move the constants around and then you can integrate it. Okay. Other questions about this? Or again, any types of problems you'd like to see other than just working through this exam from front to back? Okay. Then what else do we got? Okay. So number 3, looking at this, it looks very innocent, but you should ask, if it's on an exam, why is it on the exam? And the thing is that this is going to be an improper integral. So with cotangent, it's not the most familiar function. So I think the way to understand this, in particular, which of these is the asymptote, is a question we need to answer. And so cotangent, the way we can work through this is cotangent is cosine over sine. So if there's an asymptote, the question is, where is sine equal to 0? And sine is 0 at 0, and at pi over 2, it's actually up at 1. So 0 is where the denominator is 0. So having identified there is an asymptote here, where sine is 0, that's at x equals 0, that tells us what our limit needs to look like. So we're going to take the limit as we go to 0 from the right, because our left endpoint, the rest of the interval is to the right of it. So we're going to be integrating from t up to pi over 2 of cotangent x dx. All right. And now we need to integrate this. And for a second, I'm blanking on what the integral of cotangent is, but this is the formula sheet from last exam will also be on this exam. So we know that we can integrate cotangent, and I'm gonna look it up to make sure I get it right. And so the integral of cotangent is, so we still have our limit, go to 0 from the right, integrating from t to pi over 2, or sorry, we did the integral, so those are going to move to the other side. So the integral of cotangent is the natural log of sine x. And this is what we're going to evaluate from t to pi over 2. So the next step is just stick this in. I'll give myself some more room. And now, after we evaluate these, this is what we'll actually find the limit of. So the natural log of sine of pi over 2, sine of pi over 2 is 1, the natural log of 1 is 0, so this part's going to be 0, but we'll deal with that in case the actual limit part converges. Sorry, that's not the limit yet. This one's the natural log of sine t. So the question really comes down to, what does this part do? And for understanding this, how we can try to understand limits is, well, what happens if you just put 0 in here? So if we do that, we get this natural log of sine of 0, and sine of 0 is 0. So we're thinking, what's the natural log of 0? And here's where we start to see what's happening. The natural log isn't defined at 0. And the reason is that the natural log of 0, or at 0, the natural log of x has a vertical asymptote. So when we're taking this limit, we can write down something like the natural log of 0, but what we're doing there is not trying to evaluate it, but to write down and kind of tell ourselves, what limit behavior do we need to deal with? Well, if it was a number, we'd get a number and then be done. But since it's not, we really need to think of this in terms of what is the limit of the natural log as the input goes to 0. And that's going along this asymptote here. And so what we actually get is, since the asymptote is going to negative infinity, and there's this negative right here, the first part is 0, and the second part is going infinite. So that means that this integral, we don't get a finite number, and that means that it diverges. Okay. Questions about this problem or other aspects of improper integrals like this one? So then let's keep moving. Um, so one thing I should mention about this exam, it seems a little short. And the reason for that is not that this exam is actually going to be shorter, but this was an old exam that I gave, and the topics we covered are a little bit different. So I just removed those problems. We can expect the exam to be similar to the last exam, 8-ish problems. Some of them might be don't, or I guess in this case would be set up the integral, don't worry about evaluating it. So some those kinds of problems where it's not the entire problem, but just really the new part. So there's 5 is the last one, actually. Okay. So part 4 here is really saying that it's breaking this problem down. So what this problem is actually about is, in part B, wanting you to find the integral from 2 to infinity of 1 over x natural log of x squared dx. But for definite integrals or improper integrals, when you have to worry about the bounds, what can be a good thing to do is say, I'm going to do the integration separately and just find what that is, and then use that antiderivative for whatever you need to use it for. Rather than trying to write it out so it's all a lot of things equal to each other, just set it off to the side, handle it separately, and then come back once you have that antiderivative. And this is just saying explicitly you should do it this way. So here we want to find the indefinite integral, and I even say, here's what you should get. But in this case, if we weren't given this answer, and even I suppose with this answer, there's not a lot in it that tells you what to do, um, given this integral, we can think about which of our techniques actually applies. And the first one that you should look for is there a good u substitution? And in this case, that's really what we want to do. Um, the way to break it apart, I think, is there's the natural log squared, and then there's this 1 over x, separating um, the fractions that have been multiplied together. And especially with this natural log and 1 over x combination, originally it looks like a bunch of things mixed up, but it can be separated to more explicitly highlight that this 1 over x, that's the du to this natural log of x is u. So that's the way we'll look at this. U is going to be the natural log of x. Du is 1 over x. If that's what we make, then what we want to integrate is 1 over u squared du, or if we're going, since we're going to use the power rule, u to the minus 2. Important note, just because something is in the denominator doesn't mean it's a natural log. So integrating this, we do use the power rule. The new exponent is -1. We divide by that -1. And so then in a couple moves together, rewriting this without the negative exponent, moving this negative sign around, and then putting u, replacing u with the natural log of x, we get -1 over the natural log of x plus c. So part A, we need to do a u substitution. And then we'll get to this. So this part was the integral from 2 to infinity, 1 over x, natural log of x squared dx. So first, it's improper, write it as a limit. And in this case, unlike the last one, the infinity makes it clear which of these has to get turned into the new variable t. So we integrate from 2 up to t of our function, 1 over x natural log of x squared. And we separately did the integral, so we can just jump in and say, taking the limit as t goes to infinity, and that was -1 over the natural log of x. And this is what we're evaluating from 2 to t. The next step is substitute in, nothing too exciting there. The limit as t goes to infinity of 1 over natural log of t plus, after the negatives combine, to be 1 over the natural log of 2. And now this is what we actually take the limit. The constant stays constant, so we focus on the 1 over natural log of t. In this case, the natural log goes to infinity as t goes to infinity. So that expression there is -1 on the top, stays fixed, the bottom goes to infinity. And that kind of form, where the top is fixed, the bottom is going infinite, that means that this expression is going to 0. So this is 0 plus 1 over the natural log of 2, which means that this converges to 1 over the natural log of 2. And if you want to throw that in a calculator, you can, but this is the exact answer. Questions about this problem? Either the u substitution that I can go back and say some about, or the improper integral. So then we can do the last one. So let's find a solid obtained by rotating the region around x equals 0 and x equals pi over 4, bounded above by secant and bounded below by y equals 1 around the x-axis. So here, secant isn't the most common of functions. So we can take a little bit trying to come up with this. So secant is 1 over cosine. So one thing is that when cosine is 0 at pi over 2, we actually have a vertical asymptote. Also, cosine, the biggest it ever gets is 1, and so the smallest secant ever gets is 1. And the biggest cosine is on this region, so you have 0 to pi over 4, the smallest it ever gets is 1. And so then what happens is secant starts at 1 and then goes up along its asymptote. And it also goes up the other way, which isn't of interest for us because our integral is right here. So that's what secant looks like. This is the top of our region. The bottom is y equals 1. So that's this line right here. So we have this shape, not actually a triangle because we have secant curved on the top, but this is what we want to rotate. We want to rotate it around the x-axis. So the first few parts of getting this integral set up aren't too bad. Because our axis is horizontal, it's going to be a dx integral. Because we were told we were cutting this off at 0 and pi over 4, so those are our bounds, 0 to pi over 4. But then the question is, what are we going to integrate in here? And this is where the picture is really important, because what we need to look at is there's this gap between what we're rotating around and the bottom of the solid. So this is a washer method where we'll need to care about the distance from the axis to the edge of the inner radius, the inner edge of the solid. And then also we need this going from 0 up to the graph of secant, the outer edge of our solid. So what we need are what is this inner distance and what is this outer distance? So the inner distance is actually just 1. The bottom of our region here is the horizontal line y equals 1. So in this case, there's no curve, just it's from the axis to y equals 1. Everywhere the distance is 1, doesn't matter what x you're looking at. For the second part, we're going from the x-axis up to the curve. And so here, what this distance is that secant. So even though the part of the solid is really just this part between 1 and secant, we really do want secant x as our outer radius. the fact that we don't have this middle part is taken care of by what we're subtracting here. We want the outer radius, which is all the way from the x-axis to the graph secant, and so that's what secant x is, that distance from the x-axis to the graph. So cleaning this up a little bit, sorry, there's also a pi in the front. This is secant squared x minus 1 dx. So there, we'll go through integrating this, but are there questions about getting this set up? Which is, for this problem, the hardest part.
When you choose the big R of x, how come it's not secant x plus 1?
So the reason is that how the washer method goes is the outer radius is the distance from the rotating around to the outer edge. And so in that case, we can really forget about this line here. We're saying we don't care where the inside is, we just want to go all the way to the outer edge. And so if we only focus on this line here, disregarding the horizontal line we go through, that distance is secant x.
Okay.
Other questions? Okay. So then we need to integrate this. One thing which you might see, but turns out to not actually be helpful, is that secant squared minus 1 is tangent squared. That is true, that it is a trig identity, but it doesn't actually help us here because this is harder to integrate. So instead of thinking about this in terms of trig identities and things like that, they're subtracted, so just deal with them separately. And in fact, secant squared is something we have an integral rule for. So secant squared, its integral is just regular tangent. And minus 1, its integral is just x. It picks up the variable since it's just a constant. And so that's what we're evaluating from 0 to pi over 4. It turns out if you put 0 into both of these, you get 0. Well, obviously, you put it in x, you get 0, but tangent of 0 is also 0. And so what we're left with is tangent of pi over 4 minus pi over 4, and tangent of pi over 4 is 1. So we have the outer pi, and then 1 minus pi over 4, or you can distribute, or you can throw this in your calculator and round it to some number of decimal places, but this is the volume that we get. Okay. Questions about this problem? Or really anything now that we've made it to the end of the practice exam. I can go back and talk about some. Okay. So we have some time left before the lab period wraps up. So if anyone had any other types of problems you'd like to see, I can find them in here if you know what type you'd like, or if you had specific things that have come up in your studying or in the homework, I'd be happy to work through some of those. Okay. Then I think if there aren't any other questions, we can wrap up. I also have, I should say, big chunk of office hours tomorrow for anyone that has questions that they'd like to come in and ask me. Um, what I'm going to do after this, there are a couple extra examples I said I would record videos of. So I'm going to be posting those in the along with the practice quizzes that are in Canvas, so you can have some other examples to look at. But if there aren't any other questions, I guess we can wrap up. And hopefully this was helpful, giving you some more examples.